Hello, everyone. So welcome to video 3, or the first video about calculus. And so today I want to, in this video, I want to dive a little more deeply into this idea of computing the slope of a curve at a given point. We talked a little bit about in the previous live meeting as a kind of bridge between our discussions of lines and things like that from pre-calc and the beginning of calculus. So here's where we're going to start to really begin calculus. And I kind of motivated this idea of wanting to compute the slope of a curve at a point by discussing instantaneous velocity, trying to measure what the speedometer is reading at a given point in time, knowing the position versus time graph. And so I want to delve more deeply and more generally into this idea and actually give you some different examples of how to compute this slope or this instantaneous rate of change, both from the graph and from some algebra. Okay, so again, just going like this first little bit is about viewing what we talked about in class the other day. So here's the following definition. The slope of a curve at point P, can't write all this in the blank, at a point P, is to find the slope of the tangent line to the curve at the point P. And this, like I was saying in class, this measures the rate of change of the curve as it passes through P at that exact point, so like the instantaneous rate of change. So what's this tangent line? So this tangent line is the line that I was talking about in class. It's the line that touches the point P, right? The curve at the point P, and its slope matches the way the curve is bending at that point. So if you see in this picture, right, the tangent line touches the curve exactly at P, and the slope of the tangent line exactly matches the slope of the curve or how the curve is bending at that point. So I'm not sure as I use this language tangent line, we were talking about the instantaneous velocity example in the other day, but that's what the formal definition of the line is. So if this were like the graph of a car moving over time, right? The slope of this line P it would be exactly the instantaneous speed of the car at that particular point P in time. This is a generalization of that. So the line that's touching the graph at P and whose slope matches the slope of the graph at P, that is called the tangent line. And this word tangent, by the way, comes from the Latin word tango, or to touch. So like the dance tango. So it's touching the graph exactly in the right way at P. Okay, so our first example, kind of playing with this new idea is to measure it from the graph. And so if you have a very precisely drawn tangent line and a very precisely drawn graph on a grid, you can measure the slope of this tangent line in an old-fashioned way. What does that mean? So you can estimate the slope of the following way. You draw the tangent line, move one unit in the x direction, right? And the change in the y direction is the slope. And of course, if the change in the y direction is up, you have a positive change in y with x, so you have a positive slope. And if the change in the y direction is down, you have a negative change of y and x, so you have a negative slope. So this is very, very old school. So we'll just start, just to warm up with this. So let's look at the parabola here. So all these examples, this first example I should say, all involves the same curve, right? All involves this parabola, y equals x squared, or fx equals x squared if you like. And we're going to be measuring the tangent points, the slope of the tangent line at different points along this parabola and see what trouble we can get into here. So let's do the first one. So I'll use red. So first we're looking at the slope of the tangent line at x equals 1. So our P here is is the point 1, 1. And then the parabola is the blue curve. And of course, the tangent line, the line that's touching the parabola at the point P and has exactly the same slope as it goes along P here, through P here, is this green line. So we can measure the slope, by moving 1 in the x direction, and then seeing if we go along the line 1 in the x direction, how far have we gone in the y direction? So we've gone from a height of 1 to a height of 3. So that's the difference there is 2. And so the slope, of the tangent line at x equals 1 is 2. Right, so just old school, measure the slope of the line on a grid. You move 1 along the x direction, you see where you go along the y direction, and you see you've gone up 2. So you have, for every 1 unit to the right that we move, we go up 2 units. Slope is 2. So I'm noticing a bit of a delay in the writing, so you can just wait for it to catch up and I can adjust. Okay, give me a second and I'll try to adjust the speed. Okay, so I think I fixed the delay. So we'll look at the next example, which is again the parabola, the middle example here with the parabola. And we're looking at the tangent line, or the line that touches the graph at 0 now and has the same slope as there. So I mean, in this case, you know, as the graph goes through 0, it's bending around. It's going from coming down to coming up. So at that turn, at that instant, it has a flat tangent line as it bends from being a decreasing function to being an increasing function. So this green line is flat, right? And any flat line, I mean, it has 0 slope. A horizontal line has 0 slope. And you can see that because you move along the line, no matter which way you move, the change in y is the y value is always the same. There's no change in y. So here the slope is 0. Is 0 at x equals 0. Now let's look at the last example here. This is an interesting one, because this last example here, we want to think about p is -2, right? And so here at this point, -2. And now we notice the green line has a negative slope. So we can measure it. So the tangent line here is the green line has a negative slope. We can measure if we move from 1 unit along the x-axis to the right in the positive direction, we see that the y value along that line, right, drops by 1, 2, 3, 4 units, right? You go from 4 to 0 as you move 1 unit along the positive x direction from -2. So the slope here is -4. So you can kind of clean it up a bit. So again, we move 1 unit in the positive x direction, and we go along this green line. We see the values of the green line drops from 4 to 0 as you go 1 unit. So it's -4. Slope is -4. Okay, let's do the cubic. This is a bit of a different creature. So this is a function minus x cubed, and it looks like the blue curve on the left here. And now it's asking us to find the equation of the tangent line, not just the slope. So we want to find the equation of the tangent line at x equals 1. And for this, you know, we're gonna use our knowledge of lines from the previous video, that we're going to compute the slope like we did in these examples for the parabola. But then we know a point in the line, namely the point 1 minus 1, this purple point. And we can, once we have the slope, we can use this point to get the equation of the line by point slope form. So let's do that. Oops, sorry. Okay, so now we have to measure the slope. This is a bit trickier to do the way we were doing it before, because we don't really have enough room to the right to see the x, to see the change in y very clearly on the green line. So what we're going to do is I'm actually going to go over here, right? I'm going to go to think about 1 unit in the x direction to the left, and then look at how the y values of the green line change as I go from, this case, x equals 0 to x equals 1, we see that the green line goes from y equals 2 to minus 1. So it's this vertical distance, right? And that's a difference of minus 3, sorry. So the slope is the line, the y values drop 3, so the slope is minus 3. And then a point on the line, this point P on the line, you can see here, the purple point, which I've shaded in red, is where the line touches the graph at 1. So that's 1 minus 1. So maybe I'll use black, easier to read. So by point slope form, the equation of the line at p equals minus 1, sorry, p equals 1, or x equals 1 if you want, is y minus 1 over x minus 1 equals minus 3. So that's our slope, was minus 3. And so we get y, that's the same thing as y plus 1 over x minus 1 equals minus 3. And you can rewrite it, and you get y plus 1 equals minus 3x plus 3. And so you get y equals minus 3x plus 2. And that's our first, so now we've actually computed an equation of a tangent line from the graph, the whole thing, the slope, and using a point on the line, namely where the line touches the graph, right? We were able to find the equation using point slope form. Okay, so this next example is kind of a nice qualitative example. It's striving for us to separate two ideas. So we have different notions. People tend to confuse, when the tangent line is positive versus when the function line is positive. And when the tangent line has a negative slope versus when it has, versus when the function has a negative value. So this example is trying to get you to take apart these two different ideas. When are the values of the function positive, negative, or 0? And when are versus what it means for the slopes of the tangent line to be positive, negative, or 0. So people tend to get these things messed up in their head. And so we're doing this example just to kind of see that these are two very different notions and just to remember how to separate them in some sense. So here we have this graph, some kind of complicated graph, right? And what it wants us to do is that in the first question, for each labeled point, so A, B, C, D, or E here, indicate whether the function value is positive, negative, or 0. And the second part of the question, what it wants us to do is answer whether the slope of the tangent line at each point, each of these labeled points, is either positive, negative, or 0. And like I said, people tend to get confused with values of function versus slope of tangent line, what this means. And so we'll see in this example very carefully that these are two very different things and they're not related in general. Okay, so number one. So where is the positive? So let me just make a column here. So we'll say positive, negative, a little table, 0, and points. Little table. Okay. So where is, so what we're gonna do, we're gonna try to figure out each of these points, like if the function value is positive, negative, and 0, and we'll put these points in this column, okay? So function value. So we just need to look at these points, are they on the x-axis? Are they above the x-axis? Or are they below the x-axis? So go to A, right? A is sitting on the x-axis, which means the function value is 0 there, so we can put A in that last row. Now we go to B. B is sitting on the x-axis, so the function value is 0 there, so we may put B in that last row. Now we go to C. Now, C is sitting above the x-axis, right? C is up here, there's the x-axis. So the function value must be positive C. So we can put C in the first column. And maybe I should put this points up in the space here. There. Now we go to D. D is sitting on the x-axis, so the function value is 0 at D. Then we go to E. E is below the x-axis, right? There it is, below. So the function value is negative at E, so we may put E in this row, in this second row. So that doesn't work in E. And so that's the first question done. We're just looking at the function values. So we just want to see, is the point above the x-axis? Is it on the x-axis, or is it below? So that's positive is above the x-axis, 0 is on the x-axis, negative is below. Okay, now the second part deals with the slope of tangent line, right? So I should make another table. So slope of tangent line, sorry. Points, and we'll do, so you might maybe find this weird, but my shorthand for positive is plus iv, so it's positive. So you don't have to write this long word positive, I just do plus / iv. Negative is minus iv. So I shouldn't probably put a slash there, but positive, negative, and 0. Okay, now this is substantially trickier because now what we're looking at is the slope of the line touching the graph at these points, and whose slope is the same as the slope of the graph at these points. That's what the tangent line is. So we just can't read this. I mean, eventually get good at this, but when you first do this, you actually should be drawing the tangent lines roughly to see what the slope is. Eventually, you'll be able to do this by sight, like we did in the first question. The first part of the question, but we're not quite there yet, I think. Maybe you are. So for A, the tangent line to the graph at A is basically this red line. Let me clean that up a bit. So it's the red line touching the graph at A, having the same slope as the graph at A. That line is falling, right? So the slope of that line here is negative. So A goes in the second column. Okay. Now you go to B, and we do the same thing. We draw the line that touches the graph at B, and whose slope is the same as the graph at B. So this is a little off the point B, but make believe and make B bigger. So that's roughly the tangent line. And you notice how this is a rising line, right? So the slope of this red line here is positive. So the B goes in this column. Sorry, in this row, in the first row. So I want you to, let me zoom out a little bit. I want you to notice that both A and B, their function values were 0, but their tangent line signs, the values of the slope of the tangent line, are completely different. So these two notions are not at all related. You can have the value of the function can be 0 at the points, and the tangent lines can have positive, negative slope, and even 0 slope, but we won't see that in this example. So these notions are completely unrelated. You have to separate them in your head. Okay, let's go over to C since we're on a roll. And now I gotta draw the line C. Maybe I'll use a different color. Or C, purple and green. We can use green. So C, if I draw the line that touches the graph at C with the same slope, C is one of these points where the graph is bending around from going up to going down, like we had for the parabola above at 0, if you remember. All right. So at C, actually, as the graph bends there, the tangent line is horizontal. At that instant, the slope of the graph is horizontal. So this is 0 slope. Horizontal line is 0 slope, so C actually goes here in the last row. And now we got to do D and E, so let me zoom a bit more. So there's D. I'll do D and E at kind of the same time. And E is like this. Ugh, a little tricky. So D and E, the tangent lines there are both falling. They both have negative slope. The slope at D is a little more negative. It's a little bit steeper of a fall than at E, because as you're coming into E, the graph is starting to bend back upwards. It's not bending upwards exactly at E. That doesn't happen till about over here. So E does not have a horizontal tangent line. It has a negative tangent line, slight negative slope, but the slope is steeper or more negative at D. But we don't care about the magnitude, but we want just the sign. So these are both negative. So they both go here. So I kind of zoom out and you can see. So once you kind of do this enough, you can basically read it off the graph without drawing the lines, by just seeing where the graph is kind of rising and falling. You have to be a little careful at points like E that are kind of close to turning point, where the graph points to close to points like E where the graph is really close to bending around. There you have to be a bit you have to look more carefully. But once you've done this enough, you'll be able to kind of do this by sight. But I thought for a first go, we should be doing this by hand and drawing the lines and getting a sense for the slopes. So there we go. Okay, so now I want to move on to the next section. And excuse me. So this playing with the graphs is all well and good, but in reality, I mean, you don't often have the graph. Like, you have some formula that you've built up by understanding how something is changing. Like when we went through that example in class about speed, we said, okay, we've got a car is moving 70 miles an hour, constant speed. You know, how long is it? Sorry, how far does it travel in T hours? And we said, okay, well, we did some examples. We said, oh, that's clearly the speed times the time. And so we got a formula. And that was just VT. So it was very easy to get the graph from that. But if you like do this problem where you say you take a ball and you throw it in the air, and then you want to figure out what's the position of the ball 10 seconds later. So if you've taken some basic physics, you can figure this out quite easily. And you don't end up with a line in that case to describe the position as a function of time. It turns out to be a problem. And okay, so we could, you know, if we have we can graph the parabola super precisely, you can figure out like the slopes of the tangent lines, like in this example, from a grid. But that's incredibly cumbersome and very time consuming. So you want a very efficient method to figure out from the algebraic formula of the function, what is the slope of the tangent line at a given point? And that's what I want to start to get into now. And this is a bit of a process, and it'll take us several weeks to get to be able to do this completely. But we're going to start off small. Okay, so this is the next section. 1.3. So it's often possible to find a formula that gives the slope of the curve or the slope of the tangent line to any function, with some caveats, at any point. This slope formula is called the derivative of the function f of x. And so this is unfortunately like another terminology. Derivative just means slope of the tangent line. Okay, that's all it means. And there are reasons why you talk about it this way, but that may not become clear for a while. But what we're going to do here is to say, here's some rules. Given a function of a certain kind of form, here's what the derivative looks like. So first of all, we need some notation. The derivative of a function is often written as f prime at x, or y prime equals f prime at x. Some people do it this way. Or even, for reasons that are maybe unclear, ddx f of x. Okay, so these notations, again, I apologize, there are all these different notations. Some notations are better than others in certain cases, but for now, you're just gonna have to live with it. Maybe as we go along, we'll see in more detail why you might want to have like 3 different notations. But it's hard to believe that when you first see it. Okay, so here are the following rules. So if you have a constant function, a function which is fx equals c, this should not be a surprise, but the slope at any point, the slope of the tangent line at any point is equal to 0. So the derivative is this derivative function, which gives you the slopes of the tangent lines at any point. This is just 0 function. And that again shouldn't, if we think about what this tangent line is, right? That shouldn't be a surprise, because what does it mean to have a constant function? It just means you have a horizontal line. And a horizontal line has 0 slope everywhere. So the slope function is 0 for all x. That's all this is saying. It's not like a earth-shattering thing. Neither is the next one. So a multiple of x. So now our function fx is equal to a times x. Now let's think about this for a moment. What does that function look like? This is a lot like this is the function that we discussed in class about motion with constant speed. Right? Y equals ax is a line. So no matter where you are along the line, you have the same slope. So the slope function, or the derivative, is just constant a. You write it this way. Equals 0. Sorry, equals a. Sorry. Okay, so these two things, this constant rule and multiple of x rule, we can get from the graph. Looking at the graph, we don't have to be very clever about it. If we just remember what the slope, what the slope of the tangent line means, right? And if you have a line, I mean, the line is its own tangent. that's the slope of a line is constant no matter where you are. Okay, now this next rule is complicated, and I can't justify this to you without substantially more math. So let me do it this way. So fx equals x to the n, okay, is a power of x. Now for us, for the most part, n is going to be an integer, okay? But eventually it will be any real number, although why you want to consider x to like the root 2 is probably not obvious. So you can think of n as an integer for now. So the slope at any point x is given by the following formula. The n comes down in front of the x, and then you subtract 1 from the exponent. So this says that on this x to the n graph, right, it's the graph of x to the n, the slope of the tangent line at the point x is given by whatever that x happens to be raised to the n minus 1 instead of n, so 1 power less multiplied by n. So I think of this, when I learned this for the first time, I think of it mechanically. The n comes down in front, and then you drop the exponent by 1. And that's true whether the n is positive or negative. So if the n is negative, you're actually getting a larger negative exponent in there, which feels a little counterintuitive, but we'll get used to it. Okay. So let's do an example. So x to the 4th. Okay, what does this mean? So again, now the n is 4. So I drop the n, take the derivative. So derivative ddx is the same as this prime notation. I just didn't have room to write it, right? It's the same notation as the prime. So 4 comes down, so you put the 4 down in front of the x, and you drop the exponent on the x by 1. It's just purely mechanical. So that's 4x cubed. So what does that mean? So this is maybe not part of the question, but I want to stress this. So x to the 4th, if you graph it as like a parabola that rises, looks like a parabola. It rises more steeply, but then flattens out more towards 0. So it does something like this. So that says, this formula says, if I take any arbitrary point x on this x to the fourth curve, right? And then the slope of this line, the slope of the tangent line, the green line I've drawn, is 4x cubed, right? That's what it's saying. So maybe we should do some more examples of this in class to get used to it, but that's what it's saying. Okay, so the next one's a little bit silly. So find this derivative function for the line y equals x. So the line y equals x, gang, is just a 45-degree line in the plane. The slope of this line is 1. So no matter where you are, the slope is 1, the derivative is 1. So you could get this from this silly multiple of x rule with a equals 1, or you could get it just by realizing that y equals x is a slope of line 1. So the slope, no matter where you are, is 1, and that's it. Let me clean that up a little bit. Okay, so this is kind of, this type of question is designed to mess with your head. So find this slope function, this derivative function for fx equals pi squared. Okay, so it looks complicated, but pi is a number, and pi squared is a number. So this is actually a constant function. We're in the first case here. So this is a constant function. So f prime at x is 0. The slope is 0 no matter where you are, because pi squared is something like 9.2 or something like this. And so it's just a flat line. Slope is 0 no matter where you are. Okay, so the next one, excuse me, find the derivative of f at x is 1 over x. So for this one, actually, let me just zoom out for a second. We can use the power rule with a negative exponent if we remember the definition of negative exponent. That's what we're going to do. So first, write with a negative exponent. And you get f at x is x to the minus 1 when you do that. Right, 1 over x is x to the minus 1. Now we can apply the power rule. With n equals minus 1. All right, so go back up and take a look here. Right, so now n equals minus 1. So now the n will come down, the minus 1 comes down. That will be like multiplying the whole thing by negative 1. And then you drop 1 from the exponent. So we'll see minus 1 times minus 1 minus 1 is minus 2. So let me do it. Okay, so d dx, x to the minus 1. The minus 1 comes down in front, x times x minus minus 1. So you get minus x to the minus 2. So like I said, you get a bigger negative exponent. So if you want to write that with a positive exponent, I'm not, this isn't always necessary, but it's minus 1 over x squared. Okay, again, when you do this, the minus 1 comes down in front. That makes everything negative outside. Take minus 1, subtract minus 1, you get minus 2. And so you actually lower the exponent. Okay, so now we can talk a little bit, well, kind of tie this algebra together with this new rules that the algebra we've just developed, the new rules we've just developed, tie that together with the geometry we discussed earlier, right? So what is this derivative calculating? I kind of have alluded to this as we've gone along, but let's make it very clear. So given a function f at x and a point, oops, doesn't want to change, a point af at a, on this function, the derivative at the point, which we denote by f prime at a, is the slope, right, of the tangent line to f at the point AF at A. And that's what I was saying in that as we went along, right? In the example, right, with the x to the fourth, that this function, right, is giving you, is like a function of slopes, right? So the value of this derivative function at A, so f prime at A is the slope of the tangent line at that point. It's computing the slope for every point on the function. Okay, so now we can actually like figure, given these rules, we have a way of finding basically the equation of the tangent line at any point on a graph, so long as we can apply one of these rules. Okay, so to find the slope of the tangent line to any point on the graph, you first find the derivative function f prime at x, and then you evaluate the derivative at the point you're interested in. So at this point, AF at A. At x equals A, i.e. compute f prime at A. And so to find the equation of the tangent line, right, it's actually, once you have this information, it's very, very easy. So the tangent line will pass through the point you're interested in, AF at A, right? It's the point in question. And then you find the slope, as we did, by computing the derivative using the rules and evaluating it at A. And then you can get the slope of the tangent line, the equation of the tangent line from point slope form, like we did in one of the examples above with the cubic curve. So the point slope form gives us y minus f at A over x minus A is f prime at A. So that implies y minus f at A is f prime at A times x minus A. So y equals f prime at A times x minus A times f prime at A plus f at A, if you wanted to write it all out. But usually just remembering this is enough. Okay, and you can figure it out. You can expand it out to get what you want. Okay, so let's do an example. Now the graph here is not that helpful. The graph is just to kind of give you an illustration of what we're actually computing. So we want to find the equation of the tangent line to f at x equals root x when x is 1 over 121. Okay, so root x is the nice root curve. It's the purple curve. 1 over 121 is this point P. In the first diagram here, it's kind of a big scale. The second diagram was a much smaller scale. So you can kind of zero in on what's happening. And what we're going to do here is we're going to compute the actual equation of the green line. Okay, so we can follow these steps. So the point in question that we're interested in, so the point P, where the tangent line is touching the graph, so is the point 1 over 121, and f of 121, right? Now, what is that? Let's think about that. So it's 1 over 121, the root of 1 over 121. So that's 1 over 121, and then the root 1 over the root of 121. And you have to remember that 121 is 11 squared. So this is this point out in question is 1 over 121 1/11. Okay, so that's the point where we're going to be computing the tangent lines. That's the point where the tangent line is touching the graph and where the slopes are matching. So that's kind of step one done, right? In this little 3-point program. Oops, sorry. And now the second one's find the slope. Of the tangent line at x equals 121, 1/121. So to do this, we have to go back to this program where we need to find the derivative function, or the function of slopes for this function, the root function, that will return to us at every x what is the slope of the tangent line at that corresponding x. And then we need to evaluate it at the point in question, which is 1/121. Okay, so how do we need to find it? We need to find f prime. For f of x equals root x. Now, for this, you can actually use the power rule. I said first we're going to think about it for integers, but this power rule actually works for rational functions as well. So rational exponents as well. So this we're going to write with a rational exponent, x to the 1/2, and compute using the power rule. So here, so let me zoom back out. Where did it go? There it is. Oh, there it is. Okay, so the n now is 1/2. So we're going to bring the half down and subtract from the exponent. Subtract 1 from 1/2. Okay, use the power rule with n equals 1/2. So f prime at x, the 1/2 comes down, and you get x, subtract 1 from 1/2. You get 1/2 x to the minus 1/2. So it's 1/2 root x. And then we need to evaluate this at x equals 1/121. So at this point. So f prime at 1/121 is 1/121. So it's 1/2 times 1/111. So you flip the 11, so it's 11/2. Because 1/111 is 11. So the whole thing becomes 11/2. Okay, so I'll cross this out for a second. I'll write it again. Let's finish this down here. Okay, so now step 3, use point slope form. To find the equation of the tangent line. Okay, so the point we computed in the first step, this point P, right? And the slope we just computed here in the second step. And so we have y minus 1/11 over x minus 1/121 equals 11/2. So y minus 1/11 equals 11/2 times x minus 1/121. So this is a bit ugly algebra, unfortunately, but so that equals 11/2 times x. Now you remember that 121 is 11 squared. So this is actually minus, if you do the algebra, right, you'll be able to cancel an 11 in the bottom with this 11, leaving you one factor of 11 in the denominator. So this is minus 1 over 22. So y equals 11 over 2x minus 1 over 22 plus 1/11. So in the end, this is 11 over 2x, right? 1/11 is 2 over 22. So this is actually plus 1 over 22. Whew. Sorry. So to digest that for a second, right? Basically, once you get the slope and all, it's simple, fairly simple algebra, but the algebra is tedious because we're dealing with fractions here, right? And so what I did, I just multiplied the 11 over 2 through, and then this involves canceling a factor of 11 with a factor of 11 down here, leaving me 2 times 11, which is 22. And then just adding the 1/11 on both sides, you get 1 over 22. So what is that? I mean, what have we done? So we actually computed the slope of this green line. Sorry, the equation of this green line. So this green line here we found was y equals 11 over 2x plus 1 over 22. That's pretty cool when you think about it. And that's going to be really, really hard to measure directly off a graph. Okay, this example that I crossed out is actually much easier. So maybe you should try this one on your own. So I'll write it down here. That's what, yeah. Find the equation of the tangent line to the graph at x of y equals x cubed at x equals -2. And so you go through the same steps and you're going to be able to get the equation of the tangent line. And it's actually substantially easier than the one we just did. I mean, I can do, maybe I should do it just so we have another example. And then we can do, there's many more in the homework we can practice. So, okay, so the point in question, so the point P is -2 f of -2, right? So that's -2 cubed. And so this is -2 -8. Right, so that's where the point where the graph is, where the line is touching the graph, right? So this is the point where tangent line touches graph. Okay, find the derivative. So we need to find y prime at -2. What is the slope of the tangent line at -2? Right? Now this y prime we can get from the power rule. It's just this derivative of x cubed. So the 3 comes down, right? And you drop the exponent by 1. So it's just 3x squared. So it's much easier than the rational number, rational exponent. So y prime at -2 is equal to 3 minus 2 squared. So is 3 times 4 is 12. And lastly, I'll just do it over here. I'm kind of running out of room, but this last part's very easy. So the point slope form. So y minus -8 all over x minus -2 is equal to 12. And so you get y plus 8 equals 12, x plus 2 And you can simplify that to get 12x plus 16. So I'll let you, if you want, you can verify, you can go through this calculation and verify that last little bit there. But this is very, very straightforward. This last question, except if you deal with negative numbers, but it's not so bad. Okay, so there's a lot we covered in this video. This really is like the material for 2 classes, but you should now be able to do the first homework for this week in the schedule, which covers sections 1.2 and into 1.3. The next, I'll do one more video this week, and that'll be for this little bit more rules of differentiation that will allow us to differentiate fancier stuff. But we've done a lot for now, especially with this root graph, and we'll have a lot to talk about in the next few days. So take your time, read this. This is a pretty big conceptual jump from the stuff in pre-calc. So this whole idea of like this derivative function, right? This function of slopes, right? So where you have this fx, and you have this other function f prime of x, and at each point a, that's giving you the slope of the tangent line at that point. That's really kind of a new idea, right? So that you have a function of slopes. It's something quite new, I think, quite novel. Okay. All right. I hope you enjoyed the video, and I look forward to talking to you guys in the live meeting. That's it for now.